spaces are just the product of each.
Yeah.
1, 1, 2, 2, 2 times 2, 3 times. Yeah, but in I don't know, I never seen that in quantum. That's what you always have to sum over the 1 times 1 plus 2 times 2 plus 3 times 3.
So then you just
and
get
that's the inner product, and you just get a number. But for that you need to transpose.
Okay. I think we will have echo. No echo?
Can't you just mute it here?
Let's try. Echo? No echo.
But is it recording?
But it is recording.
No, but
Little
do you
echo?
see the sound?
Let's see if I see the sound. Yes,
Okay.
the sound goes really
No echo?
well. No echo and good sound. Thank you. So, we will be cut off from the recording facility in 40 minutes, so we are not going to be here for a long time. So, thank you for coming, considering... what are we doing? No. What should I ask? Who we are and what we are doing. So, you are serving the next generations. When we will be... So, this semester was very short, but if this course will be ever offered to you, the course project component that you are either likely or unlikely to experience. But you can make just first step and then do it for next year. So here are the images that you will get after running the codes, and it is just printout of the script that we will consider. So let's try to discuss and formulate who we are and what we are doing. Through this semester, we got several advanced techniques for modeling to solve unsolvable, right? To look on approximate methods for systems that are not easy to solve exactly. And good half of the semester was focusing on the time-dependent phenomenon. On the other hand, I don't know how about you, but I was really surprised when for the last completed set of presentations, everyone was so energetic selecting the subject of quantum computing for presentations. So it's a very narrow area. Most of us will never deal with it in professional activity, although who knows. But we can try to see if some of the approaches that we developed can be applied to such models, such materials that are inspired by possibility of quantum computing. Levi, what did you present on the subject of quantum computing?
I presented different gates. So a gate goes from one state to another. So it's like zeros and ones, but the gates can be used to use like a qubit.
Okay. Yes. I have two questions to you. First, how many qubits? How many qubits were in the model that you were presenting? Because you cannot do everything at once. You do divide and conquer, and you are presenting a model for very limited number of qubits. More than one, and less than infinity.
Which is the two systems, but I thought those two gave one qubit. Because if you have one spin,
How many total levels?
4.
Yes, so it is two two-level systems.
Yeah, two two-level systems.
And you can prove...
But then is
Yes.
that one qubit?
No.
But then how do you,
Each two-level systems is one qubit.
then you should have 16 states. If you have 2 qubits, you should have 16 states.
Why?
Because a qubit has, I thought, 8 eigenvalues that it can take. A bit and a
No. You're right now, you're mixing unmixable.
okay.
There is a standard traditional computing where you have bits and bytes, and byte is 8 bits, but those are discrete. Forget those. Now we have only bits that can exist in superposition between 0 and 1. Okay? And if you have two-level system, it is the quantum two-level system. It is a good model for this bit, for the logic that stays in the superposition between 0 and 1. If you have two-level systems, you can encode 2 such pieces of information. And if you set up Hamiltonian or evolution operator and physical mechanism for them to couple, to exchange information and to create and read information from them, it will be your oversimplified quantum computer or element of a quantum computer. So since Sam is not here, you will be answering the second question. Which physical system you were presenting as an implementation of this control node gate?
So you can do spins.
Mm-hmm.
Oh boy. You can do you can do atoms that are non-interactive, so at a very low temperature, in some medium that doesn't make it interact, correct?
Yes. You are providing...
Quantum dots.
Good.
Is this what you wanted me to answer?
But you and Sam were presenting very specific example.
Yeah.
Not first you provided an overview of all possibilities, and then you selected only one specific example.
The two-level where you have 1 1 0 0 1 0 0 1 1 1.
And they were excited and prepared and read by a laser.
Yeah,
Yes. So it is. It should be a molecule or impurity in crystal, but it is optical mindset. And one of the features in the presentation that you and Sam were doing, that the singly excited state is degenerate, right? Suppose if you have 2 unique two-level systems, then there will be total 4 states with 0. Then second state will be degenerate when either first or second is excited, and then fourth state when the system is double excited, when both of them are excited, right?
But
four levels, but 2 and 3 are degenerate.
They're not the same.
But in order, if you want to implement the gate that will be practically interesting, which will be non-trivial and useful for applications, you need to lift the degeneracy a little bit.
Yeah.
Okay?
So you're saying they're not degenerate or they are degenerate?
It is so much simpler simpler to start with degenerate.
Okay.
But then, if you want to model a real, something that has a connection to real life, you need to lift this degeneracy. But the main intellectual challenge is to develop approach to deal with any change of, to track quantum state of two level systems when they're coupled, and implement operations that will liberally excite or transfer excitation from one system to another. In the available time limit, which is shrinking and shrinking and shrinking, we have only half an hour left, we will not be able to do everything. We will be only able to make first steps. So what we need is to set up a basis, set up more typical operators, formulate Hamiltonian evolution operator, and see how superpositional state, which we can either create by optics or we can set it up as initial state, evolves with time. And then if we get fluency in such skill, then later we can modify parameters of such modeling tool to apply it to more practical applicable systems. Right now, we will just proof of concept. Any questions right now? Do you see the connection? Good. So how do we formulate our toy problem? Let me suggest the following setup. Zoom out. No? Zoom out. Zoom in. So we are going to deal with model of two level systems. Right now, we will set up their frequency the same, but since it is a parameter, we can easily change it to whatever we need. So we may model the excitation or de-excitation driving the system by optical pulse. And in addition, we may consider probability of excitation transfer from one to another. The process when one system experiences instantaneous relaxation and another experiences instantaneous excitation. So there is a chance, if they are close to resonance, that excitation will go forward and backwards. So if we take into account all these mechanisms, we will be just opening door to further modeling. We will not be reporting ready-to-use quantum computer today. But do not expect it. But if we complete the steps, we will be able to model quantum computers maybe tomorrow, or tomorrow in a general sense. So what is important for us is to be able to track the, let's call them A and B for system 1, A and B for system 2. So two things. We need to be able to describe superpositional states, and we need to select the observables that we will target and describe. So for the basis states of the overall system will be composed as product of the state of individual systems, and our Hamiltonian will be 4 by 4, right? Good. And for observables, we, since two-level systems are following the same algebra as spins, we may select the operators that are equivalent to spin of system 1, system 2, and overall spin of the whole system. So we can work on the system first, x, y, z, system 2, x, y, and z, and total x, y, and z. And we may want to set up these operators, and then after we run the dynamics that changes the system during along the time, we may compute those as observables. So to see if how does the superpositional state evolves in time and whether it maintains its superpositional state properties. Make sense? More or less? So I suggest that we specify the interaction by some constant and then follow the dynamics of these expectation values over time. Maybe since there are too many of those, like 9, we can plot them as a point on or inside blocks here. And there should be 3 spheres. One for system 1, another for system 2, and the third one is for their sum. And this summation, vector sum, somehow relates to the very first chapter that we covered in the first chapter of this course, addition of angular momentum. So in some sense, after we pursue this little exercise, we will be able to illustrate addition of angular momentum from time domain perspective. What do we expect? What do we expect if we follow this plan? Any ideas? So if we create system not in the superposition, if we create system 1 in excited state, and we implement the coupling between them, then as time passes by, the excitation will jump from one to another. What will happen if we create it halfway? Probably. How would it look on the blocks here?
It would be much more equilibrium.
Probably for each individual spin, it will perform a trajectory on a surface, but it will be like two pendulum going in opposite phase. When one goes up, another goes down, and opposite.
But wouldn't it be more towards the equator? So it wouldn't go all the way down. It would stay more on the, like towards here. Because if you had full inversion, it would go all the way up. But if you don't, if you do like a half high pulse, it only goes halfway.
Mm-hmm.
So then wouldn't it stay somewhere along the?
Probably it will not go into upper portion of the sphere, so it will be below equator. But let's compare our intuitive expectations with modeling and quickly go over the script.
No, you're being ridiculous. It is the speed of an electron in a core, not the speed of light. No.
What Brendan suggests?
He said the reason why the screen has multiple and there's a delay is due to the speed of light.
Come on.
No.
Can you see 3 times 10 to the 10 meters per second? I sure can.
That's all in the camera and the screen.
How far is this? How far is this? Like 2 meters?
Back to the camera, computer.
Yeah, most of it is electron going through the wire.
And then it goes through amplification cycle.
Yeah, it's the electronics.
Yeah,
the current is also.
And here it goes to the router that is hopefully in this state.
it could be right over there.
But it could be like in Minneapolis. Well, if it goes around the globe, what is the delay? I think it is still fraction of a second.
In the Wall Street, they used to use fiber optics, but then they made fiber optics really long, so that people couldn't use it. So now they're using radio waves to go, and it's much faster.
Oh, what?
It's raining. They're using radio wave powers, so they set them up, and then they send a radio wave, and then they send it in through the regular cable, so then they can speed it up.
Okay, we'll continue this discussion soon. Let's go through the script, if you don't mind. Okay, thank you. So setting up the parameters, the dimensionality of the system is 4, and then it is just illustration of what is our basis, one excited, another excited, and then we may set up initial state that we will propagate later. So the first, second, third, and fourth states, and we keep them normalized. And first and second means that the second system will be in the ground state, and first will be in the superposition between ground and excited. Then, if you want to formulate Hamiltonian, I suggest that we set up operators of creation and annihilation for both of the systems, and this creation and annihilation operators will work this way. If it is operator, let's say SM, S minus, annihilation for system 1, then for this quadrant, from here to there, it looks like regular 2 by 2 annihilation. And then it is multiplied by unitary operators. For the second quadrant, it looks also as a annihilation operator. So it means that it changes first system and doesn't touch the second. And same idea for the annihilation for second system. So we need to look this one, skip here, take this one, look here and there, right? Skipping over this the place. So this will be our 2 by 2 matrix that affects second system. And here is another one. So it's like it, no, 2 by 2. So let's skip this line, this line, this line, and this line. And then it will reduce to 2 by 2 matrix. Right? And as soon as we do this little intellectual effort, we can do creation operator just by transpose and conjugate. And then we also may install the identity operator. Good? Now, if we recall what we did in Quantum 1, as soon as we have creation and annihilation operators, we can quickly set up both, not both, all spin projections. For Z projection is plus times minus, subtract minus times plus for first and second spin, and for the transversal operators X and Y, it is just addition of creation and annihilation or subtraction with the imaginary factor. And then we can also formulate the total spin just by angular addition. Then we can prepare building blocks that will enter into the Hamiltonian. Like if you want a term in the Hamiltonian that will flip spin, that will correspond to energy transfer, it will be annihilation in one and creation in second, plus opposite. Annihilation in second, creation in first. And if you want optics, if you want the Rabi oscillations, then we have just Sx times intensity of the field, if we are in the interaction picture. Then these parameters are not so important, they are technical details. Then, in case we do not have any interactions, then we can formulate Hamiltonian as energy of system 1 times Sz plus energy of system 2 times Sz for Z projection for second. Right? Diane would approve. It is what people do in physics. Good. And if you have several interactions, we just add together terms in the Hamiltonian, which we can do. But in case we consider interaction picture, then the simultaneous flip of this quantum states will include only this term in the Hamiltonian. Let's keep only this term for the beginning, as it transfers coherency from system 1 to system 2, and then if needed, and if time allows, which is probably not the case, we can put the whole enchilada, all terms, and see what happens. Then the approach is standard. If your Hamiltonian doesn't depend on time, you diagonalize it and expand your initial state over eigenstates of the Hamiltonian, and then this C is expansion coefficient of it is a scalar product of initial state times eigenstate. and it uses as a decomposition of initial state over eigenstates. Then we add together this expansion. So this is a standard thing for basic quantum theory. Expansion coefficient times eigenvector times oscillating exponential, right? And if you add together all eigenstates, then you get the solution. Psi as function of t. So here is as numerically correct solution. You can build it for any Hamiltonian, but then what do we do with it? We need observables. And then we can set up the operator corresponding to observable with bra and ket on the left and right, which is done here. Like projection of spin times ket, and then it is multiplied by bra from the left. And in this way, we can get all three projections for spin 1 and spin 2. But here, it is this expectation values is state of spin 1 upon average over state of spin 2. In some sense, this operation is very similar to what we will be doing in class tomorrow, performing average over heat bath. So making average for the state of system 1 over state of the rest of the world. But here the rest of the world is relatively poor. It's just another spin. Tomorrow it will be something more liberal. Okay, and after we are done with computing of these things, we can just plot them in a way Levi has suggested, like parametric plot of three functions, and then you were telling me how to change the radius of sphere, but I didn't remember. You probably can modify the code and send it to all of us.
But you just multiplied it by 2.
Yes, yes. I multiply the vector by 2 so that the end of the vector hits the surface. So where is the... So plot 3, which means three-dimensional plot, parametric plot of these three components. So after, please try to run and see what happens. This code works much quicker compared to the previous codes that we did for density metrics and
Oh boy.
so if you would have a little more time, we could convert these images into animated movies. But the initial state, so here is our output. 3 spheres, each of which correspond to projection of spin projections of first system, second system, and then the total spin. So based on the initial state, both systems starts halfway. No, the first system starts halfway between ground and excited, and the second will start at the south pole, and then there will be oscillations. When this one goes down, the second one will go up. So they will be oscillating with shifted phase.
I'm trying to get the half radian right. I think it has to do something like x, y, z is equal to sphere. And then you just say plot a, x over a, y over b. I said 1, 2.
I see.
I guess I should say. Oh, you can't do a multivariable. Oh, no, that works.
So there is one of yeah. And we explore how the outcome changes if you what you can well when you try this code you try to break it on pieces.
It works to do a half that way.
So you may change the initial condition and you may change state for the third.
No, I just
Explore the concept.
here.
No, I'm telling for not just exploring the
When you plot the sphere, though, you just say sphere and that plots it?
yes.
Oh.
So is this continuously getting
Yes.
high pulse? So that it keeps oscillating back and forth?
Mhm.
Okay. I was trying to think how would it keep oscillating back and forth if there was no energy input.
Well, we have disabled the preparation of initial state. We know how to do it. We did it for the like third of the course on the labs. But now instead of modeling the laser pulse, we just set up superposition that can be considered as created by PyO2. Right?
So it's already started off in
Yes.
the 90 equilibrium with the middle state.
Yes.
Up in-
Yes.
or halfway
Well,
through.
superposition.
Yeah.
That's the worst sphere I've ever seen.
Let me formulate a question that you can answer numerically, or you can just get it. Which type of dynamics will we observe if the system is either in both spins are in both systems are in ground or both are in excited? Will you see any dynamics for the Hamiltonian that we started to consider? The energy transfer Hamiltonian, one goes up, another goes down. What if we create system in the state zero, both are zeros, both are ground state, or both are excited states? Will anything change this time?
Are we considering interaction with the bath?
No. With the model that we have, there is no. Right now, we don't have that.
I don't think anything.
Right now, in the superpositional state, or if you will you see any dynamics if both systems are in ground state?
I don't think so, but I might be wrong.
Let's check and put initial state instead of square roots, put 1, 0, 0, 0. Bless you. So to answer this question, I'm going to the very beginning.
You can just online put it to
Yes. Just remove the percent from line 32, correct. So there is no line. If you inspect tightly, you will see that both there is no trajectory. There is just point on the south pole.
That's a -1.
-1 if you multiply it by 2, or if you do not multiply by 2, then -1/2. So in order to launch this interaction, at least one system should be excited. Any questions about this stuff? What would be your assignment to the next generation of students based on this code? Yes, because everyone is so interested in doing something with the code that you are ready to do. So, what entertain you with the question?
I maybe. Do you know if this code will work if they're not degenerate states?
It should work, but first we need to, as soon as it is non-degenerate, we need to bring in the H0 Hamiltonian, the detuning. Even if we are in the interaction picture, then this delta on the diagonal will appear. Plus delta for system 1 and minus delta for system 2. And then the vector will start equatorial motion. Yes, yes, yes.
That would be cool.
You can do it in the remaining 3 minutes.
Oh. But couldn't you just have them figure out how to write that and then have that like a mini project?
No,
Or is that like two things? Because I couldn't do it if I you told me to do that.
I'm considering it as a longer project with more discussing and designing rather than doing simple assignments.
No, but if you just give them the code, then that would force them to read through it and understand what's happening versus you just saying this happens here, this happens here, this happens here. So since you already have it, I'm assuming you're not going to do lab in the first week.
No, it will be like 60% from the beginning, leaving like 60% of time from the beginning, leaving like last 5 weeks for the project.
You teach for 7 weeks, and at like week 8, you start the labs.
Yes.
But you could give them this earlier and be like, hey, try and encode this.
It can be done, but if you do incrementally, looking on simpler codes first, if there will be no, we have cancelled 3 weeks in this semester because of conferences, or maybe even 4. Therefore, total number of hours.
Oh, yeah, yeah.
Sunnable, physics, physical.
APS was doing three.
Okay, then 3.
Wasn't it?
Yep. So if we keep only the accumulation of phase, then it should just rotate around the equatorial lines. Here it is. And if we look together for both accumulation of phase and transitions between, save it first. Save.
Oh, so you already told it. You just have to comment.
Oh, yes. Then it will be a little hard to analyze based on the static figure. Probably one needs to make it more dynamical to see like a point moving with time. But if you want to model the gate, we need to bring in the degeneracy and sequence of pulses. So it will be a little more complicated than this code. This uses static Hamiltonian, and all codes that we were doing before, it was propagation forward in time with time-dependent Hamiltonian. Any questions? Do you feel inspired?
I feel inspired to do some non-adiabatic dynamics.
Good. This code can be also used if you explore the energy transfer between chromophores or quantum dots. It's just tuning the parameters. When we were shopping for presentation subjects, you declined last one in the list because I didn't explain it in details. I thought something about pair of quantum dots, and you thought, no, I'm not doing it. But this math can be used for like, energy transfer in array of quantum dots. I don't have anything to tell. Thanks for the camera. Last weapon semester.
Showed up. See, I told you it's a speed of light.
Yes, we all are moving quicker than speed of light.
It's slower.
Okay, let's adjourn and meet tomorrow. Yep.